So in this next series of lectures, we're going to look at several ways to find antiderivatives of some trigonometric related functions. For example, in this lecture, we're going to look at integrals of the sine and cosine raised to a power. We're also going to look at the tangent, secant, some other functions raised to powers. We're also going to look at situations where we have the product of some trigonometric functions. So let's take a look at this thing here. Integral of sine to the fifth x dx. What I'm going to do here, and I would do the exact same thing if I had a cosine to the fifth here, right? I would do the same thing. So what I'm going to do is I'm going to peel off one of those signs. So I'm going to make this the integral of the sine of x times sine to the fourth x dx. All right, now that's sine to the fourth. That's sine squared squared. So I'm going to make this the integral of the sine of x times the sine squared of x squared dx. Okay, but sine squared, that's 1 minus cosine squared. You'll see why I want to do that, why I want to make that substitution in just a second. I'm going to make this the integral of the sine of x times 1 minus cosine squared x squared dx. Now here comes the calculus oriented substitution, right? I'm going to let u equal the cosine of x. All right, so that means du equals negative sine of x dx. Notice I've got a sine of x and a dx in there, right? So what am I getting? Let's move the negative sign over. Sine of x dx equals negative du. So now I'm going to do the substitutions. I'm going to replace the sine of x and the dx with negative du, and I'm going to replace the cosine with u. So this is 1 minus u squared squared. And that's just a polynomial, right? I'm going to multiply this out. This is negative integral u to the fourth minus 2u squared plus 1 du. And this, I can do this integral, right? This is u to the fifth over 5 minus 2u cubed over 3 plus u, and I still have that minus sign out in front, right? Plus a constant. All right, now let's go back to cosines, right? Put cosine back in there for u, and I'm going to distribute that minus sign at the same time. So this will be minus cosine to the fifth x over 5 plus 2 cosine to the third x over 3 minus cosine of x minus a constant. And that's my antiderivative. Now sometimes you'll see people, they don't like, for some reason, having a minus in front of the constant, so they might replace this with another constant plus d. Doesn't really matter to me one way or the other. Either way, this is our antiderivative. And if I had cosines there instead of a cosine there instead of sine, I would do exactly the same thing. I would pull a cosine off, and then replace cosine squared with 1 minus sine squared. And you do the exact same u substitution over here. All right, so how about this one? Sine to the fourth dx. Well, you see, this one is a little different, right? Because it's an even power, so I don't have that sign that I can peel off to kind of be the u substitution part, like I did on the previous example. So I am, however, going to do something very similar here. I'm going to rewrite this as the integral of sine squared x squared dx. And I'm going to use another trig formula. I'm going to make this the integral of 1 minus cosine 2x over 2 squared dx. Okay, now let's multiply this out. Right, let's multiply this out. The denominator is going to become a 4. I'm just going to pull that 1/4 out in front. And this will be the integral 1 minus 2 cosine 2x plus cosine squared 2x dx. Okay, now we're almost there, right? The 1 I can do, and the 2 cosine 2x I can do, but that cosine squared 2x is a problem. So I'm going to pull out, I'm going to use almost the same trig formula, right? I'm going to use the one for cosine squared, and this will become 1/4 the integral 1 minus 2 cosine 2x plus cosine squared 2x. This is going to be 1 plus cosine 4x over 2 dx. And now I'm home free. Right now I have it in just in terms of cosines, and I can do that. So let's clean it up just a little bit more. 1/4 integral. I'm going to take this 1/2 here and add it to the 1. So that'll become 3/2 minus 2 cosine 2x plus 1/2 cosine 4x. It's a dx, just barely squeaking in there. Okay, now I can do the integral parts. This is 1/4 3x over 2. Yeah, I know that's a weird thing to show up with a trig thing, but there it is. Minus sine 2x plus 1/8 sine 2x plus a constant. Right, and that's kind of it. It'd be a little cleaner if we distributed that 1/4 in there. So we can make this 3x over 8 minus 1/4 sine 2x plus 1/32 sine, whoops, this is a sine 4x here, not 2x, sine 4x plus, okay, 1/4 c. We really wouldn't write a constant times a constant like that. What I would do here is what I just mentioned on the previous slide. I would make this plus another constant d. You really don't want to use c again, right? Because it really isn't the same constant once that 1/4 goes in there. But we can always just replace it with another letter. Okay, so that's it, right? That's my antiderivative. So I'm just summarizing what we did here, right? If you have an odd power of the sine and cosine, like we did in the first example, split off one sine or cosine, then you use the Pythagorean identity to convert the remaining even power and do substitution. If you have even powers of the sine and cosine, then you're going to use one of the two half-angle formulas, sine squared or cosine squared, and you're going to do it repeatedly. I had to do it twice in the previous slide until at the end you've eliminated all the exponents, and then you should have all just sines or cosines of some multiple of x, and you can do the antiderivatives of those pretty quickly. So in the next lecture, we're going to continue this discussion of methods for finding antiderivatives of trigonometric functions. We're going to kind of expand on what we did here, and instead of looking at integrals of powers of a single function, we're going to look at how to find antiderivatives for integrals of functions that have multiple trig functions multiplied together, again, with exponents.